Hello, and thank you for coming to my presentation. My name is Tanya Cochran, and I will be doing water toxicity and marine predators, the mercury exposure in sharks. I hope you enjoy. Good afternoon, everyone. My discussion today will be on mercury bioaccumulation in marine top predators, sharks, and what it means for sea and human health. To guide this discussion, my research question is, how does mercury build up in shark populations? And what does this tell us about the broader health of our oceans? Sharks are at the top of the marine food chain and are therefore living indicators for environmental pollutions. These long-lived predators can become exposed to contaminants over time when they are introduced into the ecosystem. Thus, knowledge of mercury in sharks has implications for marine biology, but also for seafood safety, health safety issues, and conservation policy and pollution control. First, we will explore the pathways of mercury entering marine food webs. Mercury contamination is relevant because it can bioaccumulate in marine food chains to a higher magnitude in top of the food chain consumers like sharks. First, it is found in oceans in the form of mercury, and the microbes transform it to the most highly toxic and bioavailable form, namely the methyl derivative of mercury, MEHG. Moreover, biomagnification occurs as MEHG processes up the food web, meaning that predators tend to have much higher concentrations than their prey. However, around 88% of total mercury in Atlantic sharks was found to be in the form of methylmercury. Furthermore, this accounts for the disproportionate toxic loads found in the body of apex predators and the reason mercury issues are relevant for the health of the oceans, the safety of seafood, and human health. To explore the potential for non-lethal capture techniques to assess exposure to mercury, researchers employed small fin clip capture combined with carbon and nitrogen stable isotope analysis. In particular, the ratio of N isotopes reflects the position of the animal at the upper trophic levels, and the ratio of C isotopes reflects the animal's foraging habitat like coast, pelagic, and reef habitats. In addition, isotope information can be used with mercury levels to help researchers identify whether diet or habitat age or migration changes may affect exposure to mercury. The method was used on a shark dynamic system at a marine protected area of the Refugio archipelago off Mexico's Pacific coast. Results confirm that shark length was the major factor affecting HG concentrations in the Revillagigedo shark community, suggesting that bioaccumulation was more responsible for mercury levels in sharks than diet and particular habitat selections. This means that bigger and older sharks tended to have more mercury in their bodies over time. In addition, a recent systematic review of 78 European studies revealed that apex predators, such as tuna, swordfish, and sharks, were some of the most likely species to contain levels of mercury that exceeded legal limits. In particular, the short-finned mako sharks larger than 190 centimeters and blue sharks larger than 250 centimeters made the EU regulatory limit. Furthermore, when consumption of silky shark was used, the hazard quotation ranged from 5.7 in North America to 38 in Asia, which exceeds the safety level of 1. These findings are thus raising new questions for ocean health and human health. These results provide an insightful constraint on the effectiveness of marine protected areas. There is no complete protection of sharks in MPAs. No clear protection effect was found as migratory sharks transit between protected and exploited areas, further exposing them to contamination. Hence, mercury pollution is not limited to a local polluting problem, but a good environmental problem. Furthermore, there is a human health aspect to the issue, as the World Health Organization placed mercury in its top 10 list of chemicals of public health concerns. Seafood can be harmful for those who are pregnant, children, and elderly. Selenium actually provides some protection against mercury toxicity in certain species, but not all. Finally, 3 conclusions can be drawn from this research. First, biomagnification. It's the highest risk in the largest and most lifelong organisms. So, redundancy may be a more important factor than location. Size or age of the shark may be more important than where it comes from. Second, this is a global pattern and not an isolated regional problem from the Pacific to the Mediterranean. Finally, mercury protection in marine zones is not the sole answer to the problem of mercury pollution. A proper answer must actually take action against pollution at the source. Thus, continued biomonitoring, stricter global mercury emissions regulations, and more transparent seafood labeling are crucial to enable consumers, particularly vulnerable consumers, to make choices. I hope that my presentation has been very insightful and informational. And I am glad that you stuck through this presentation with me, and I really appreciate it. Thank you and have a good day.